Analyzing gender bias in audio deepfake detection through one-class VAEs. Deepfake technology introduced a wave of deepfake media that make it hard even for humans to distinguish generated and real images in audio. This leads to the spread of fake news, harassment, and false information. The question we'd like to explore is the possibilities of attribute bias that could affect the performance of VAEs for audio deepfake detection. Counterfactual fairness of the model can be assessed by comparing the outputs that were reconstructed using the actual value and a counterfactual value. In our case, the gender variable is appended to the latent space vector before it is passed on to the decoder. The dataset that we used was from ASV Spoof 2019 Logical Access. Real and deepfake speech from 20 speakers is included in the training and dev datasets, and 6 different devices and methods were used to create the deepfake audio. This table shows the number of real and deepfake audio in the training and dev datasets. Due to the imbalance of the data, we created our own training and dev datasets by concatenating the original training and dev datasets, then split the new dataset into training and dev. This way, instead of training only on 2.5K data, we could train on 4K data. It is essential to train on real data because deepfake data are generated from many different algorithms and devices. We train a one-class VAE on real audio data. After the data is encoded and reparameterized to produce a latent space vector, the actual gender value and a counterfactual value is appended. Each of these vectors is decoded, and the mean squared error between these outputs is computed to determine whether there is a significant difference between them. During learning, the loss function used is the sum of the binary cross-entropy between the reconstructed output of actual data and the Kale divergence of the mean and variance of the encoder and the normal distribution to push the mean and variance of the encoder towards a standard normal distribution. During training, we collect the root binary cross-entropy error from training data and store them in memory. During prediction, we compute the RBCE of testing data and compare them against the threshold from the RBCE of training data. If the RBCE of the testing data is greater than the threshold, we predict 1 for deepfake and 0 for real. Our network consists of an encoder and decoder with 5 convolutional layers each. Each convolutional layer has batch norm, Rayleigh activation, and dropout layers. The output of the encoder is passed through 2 fully connected layers that are used as the mean and variance vectors for reparameterization. The output vector of reparameterization is concatenated with the actual gender value and the counterfactual gender value and is then decoded. For evaluation, accuracy and F1 scores are both used to measure the performance. Using F1 scores is important because it accounts for the label imbalance in datasets, which is inherent in the ASV Spoof 2019 LA dataset. RBCE and MSE of each gender is studied to determine whether the model is biased towards a gender. The difference in means of the RBCE of real and deepfake audio is studied in hopes that the difference will increase as the model learns the distribution of real data better. After hyperparameter tuning, we determined that threshold value of 65 and latent size of 512 produced the best results. We achieved 70% accuracy and 0.79 F1 score on the test dataset. The difference in the means of RBCE for real and fake data continually increased, showing that the model was learning the distribution of real data well. In conclusion, the question of interest was whether the gender of the speaker affected the performance of the variational autoencoder. We expected the mean RBCE of the 2 genders to be similar. During the first epoch, we see that the distributions for both real and fake data are bimodal. We identified that this difference was due to gender. As the model learned, the bimodality disappeared for real data, but not for fake data. However, the conditional RBCEs above and the means of the 2 modes in the histogram show that the bimodality after training is not due to gender, and we concluded that the bimodality occurred as a result of the fake audio coming from multiple different sources and thus different distributions. Thank you for watching.